Hey everybody, in this video we're going to go through section 3.3, which is all about the Solubility Product Constant, or KSP. So make sure you take some time to read through the meme here because it's obviously hilarious, okay? It says, a physicist, a biologist, and a chemist went to the ocean for the first time. The physicist saw the ocean and was fascinated. He said he wanted to research the fluid dynamics of the waves and walked into the ocean. He drowned and never returned. Now, the biologist said that they wanted to do research on the flora and fauna inside the ocean and walked inside the ocean. They too never returned. The chemist waited for a long time and wrote the observation: physicists and biologists are soluble in ocean water. Of course, being hilarious because this ties nicely into our solubility unit. And in this section, we're actually going to link the ideas from our equilibrium constants with the constant of solubility. So we're going to be looking at the solubility product constant, keeping in mind that there's nothing different from this than there was in Unit 2 when we looked at those equilibrium constants, because we still have an equilibrium in this unit, and it's because it's between our dissolved ions and the equilibrium between the dissolved ions and that crystallized solid that forms in the solution. So we're going to be looking at that in saturated solutions. So our goals for today are: we're going to write the solubility product expressions for ions dissolved in water. We're going to calculate KSP from solubility. We'll calculate solubility from KSP, so kind of take it backwards, and explain how to experimentally determine KSP. You'll see some wording for that in the questions, and we're going to do a lab on this later on. So first problem here says, write out the equilibrium constant expression for a saturated solution of magnesium chloride. Okay, so the first thing is we've got some key words in the problem here that are going to tell us a little bit about the problem. First off, you'll notice that it's a saturated solution. When we have a saturated solution, we know we have an equilibrium. So we're going to go ahead and we're going to write a net ionic equation for looking at magnesium chloride. So I'm always going to start with the solid when I'm writing solubility product expressions. So I'm going to go with my magnesium chloride here, MgCl2. So we know that we need 2 chlorines to balance the charge, the positive 2 charge of the magnesium. And I'm going to show that reversible arrow because we are in equilibrium here, because we've got our saturated solution, and it's in equilibrium with the magnesium ions and the chloride ions. And you'll notice that we've got a 2-to-1 ratio with the chloride ions because of that subscript 2. When they split apart, we get 1 ion of magnesium and 2 chlorides. And I'm just going to go through for a second. We're going to just look at what this molecule looks like. If this is my magnesium, and here's my chlorines, I've got 2 chlorines attached to 1 magnesium. So that's kind of what the molecule looks like. So when this splits apart, it creates 1 molecule of magnesium and 1 ion of magnesium and 2 ions of chlorine. And this is really, really important concept here because we've got a 2-to-1 ratio, and we're going to be looking at these ratios quite a bit when we're doing some problem solving and questions. So there's my net ionic equation. The magnesium chloride, when it's in together form, that's the crystalline form. So I'm going to put a solid there, and the ions are aqueous. And a reminder that that crystal is splitting apart because of the hydrogen bonding of water. Water is a polar molecule, and so the hydrogen ends of it take on a slightly positive charge, and they're going to surround the chlorines. The oxygen takes on a slightly negative charge because it's more electronegative, and it attracts those electrons from the hydrogens, and it's going to surround the magnesium there, and so that's what splits those ions apart. So you'll notice that because we have an equilibrium here, we can write an equilibrium constant for this. We can write a KEQ expression. When we write our KEQ expressions, we always put the products over the reactants. So I'm going to show I've got the concentration, that's what the square brackets mean, concentration of magnesium multiplied by the concentration of chloride ions, and that 2 there becomes a power. So the coefficients become a power, And usually we're going to take this divided by the reactants, but because my reactant is solid, I'm going to leave it out. So my KEQ expression just becomes the two multiplied by one another. And because we have a very special scenario, we're talking about solubility all the time, you'll notice that these are multiplied. In other words, it's a product of those two multiplied. We call it a solubility product expression. So there's the expression. So the saturated solutions are a special type of equilibrium, like I just mentioned. A new name is given to that equilibrium constant. So when we take our KEQ, we can kind of subdivide that into things looking at concentration or looking at partial pressures. We're dealing with concentrations here, and we're going to look at some special types of equilibrium constants. One is the solubility product constant that we just kind of derived. We're also in the next unit going to be looking at acid dissociation constants and base dissociation constants. So they're kind of all in the same family of equilibrium constants. So you'll notice that on the next slide here, I just have a generalized form of what we've just done with deriving our equilibrium solubility product constant for our solubility equilibrium. I'm starting with a solid here. On the other side, I've got my aqueous species. So very important that we start with the solid so that we end up with a product constant. And aqueous on the other side. A here is coefficient and B is another coefficient. And you'll notice that those coefficients become powers in my expression. So there's the generalized form of my equilibrium solubility product constant there. So we're going to do a couple of examples so we get used to working with these KSPs. The first is calculating a KSP from a solubility. So in this question, we're just going to start off a little bit easy. We're looking at molar solubility. So this is the number of moles that can dissolve to create a saturated solution. The molar solubility of calcium sulfate is 8.4 times 10 to the negative 3 moles per liter, capital M. Calculate its KSP at that temperature. So we're going to start off a question like this by writing out our solubility product expression. So I'm going to take my calcium sulfate, CaSO4. I'm going to start with it as a solid, and I'm going to write an equilibrium expression here, showing it splitting into its ions. And you'll notice that those ions are aqueous. So when we write our solubility product constant expression, KSP, we're going to take the calcium ions, and its coefficient is 1, so I'm not going to put any exponent on there. And SO4, sulfate also has a coefficient of 1, so I'm not going to put any multiplier on there either. And now what we're going to do is we're going to plug in, we know that the molar solubility is 8.4 times 10 to the negative 3. So if you think about that, that's the number of moles that are able to dissolve to create that equilibrium. So when I start with 8.4 times 10 to the negative 3 moles per liter of that calcium sulfate, the calcium sulfate is going to split up in a 1-to-1 ratio. So my concentration of calcium is going to be the same because we're in a 1-to-1 ratio. It's going to be 8.4 times 10 to the negative 3 moles per liter. And the sulfate is going to do the same thing because it's a 1-to-1 ratio. So I'm going to substitute that into my KSP expression. KSP is equal to 8.4 times 10 to the negative 3 times 8.4 times 10 to the negative 3, or you could take 8.4 times 10 to the negative 3 squared if you want. And when I put that in my calculator, KSP is equal to 7.1 times 10 to the negative 5. And our KSP, just like with our KEQs, the units really don't give us any extra information, so we don't include units for that. So there's the a kind of a simple example where we're given molar solubility and we're calculating KSP. We're going to take another example here, only this time we're going to notice a different ratio with our moles. So it says the solubility of lead 2 chloride is 4.4 grams per liter at a certain temperature. So there's a couple of different things going on in this question. Number one, instead of molar solubility, it is giving us grams per liter. So this is showing us how many grams can dissolve per liter to create that saturated solution. So lead 2 chloride, PbCl2, we'll write out the net ionic equation showing how that dissolves in the water. I'm going to have Pb2 plus 2 Cl minuses this time. Okay, so you'll notice that we've got 2 ions of chlorine for every 1 ion of lead this time. So my KSP expression is going to be my Pb2 multiplied by the Cl minus, but this time I'm going to take that 2 coefficient and I'm going to turn it into a power. Okay, so now you'll notice that this KSP expression, the solubility product expression, those square brackets mean we need a concentration. We need moles per liter. And I'm given grams per liter in this question. So we're going to have to do a little bit of legwork to find moles per liter first. So we're going to go back to kind of our stoichiometry for a second here. So I'm going to take 4.4 grams of lead 2 chloride per liter. And I'm going to divide by the molar mass of lead 2 chloride. So I'm going to go ahead and add that all up. I get from the periodic table 213.2 grams per mole. You'll notice that the grams cancel out, and I'm left with moles per liter of PbCl2. So I got 0.0206 moles per liter. Now, when I look at the ratio of this, this is the concentration of PbCl2. So PbCl2, you'll notice that I've got a 1-to-1 ratio with the lead ion. So my concentration of lead ions in that solution is going to be 0.0206. But with the chlorine, it's double that because of that 2 coefficient. So I'm going to actually take that times 2, 0.206, multiplied by 2 gives me 0.04128. Okay, and I'm not rounding in my calculator, so that's why I get something a little bit slightly different. And then I'm going to substitute those into the KSP expression. So KSP is equal to 0.0206 multiplied by 0.04128, oops, squared. Put that all into my calculator, and I get a KSP value of 3.5 times 10 to the negative 5. So a slightly more complicated question there, but still definitely doable. Remember, this is just like our equilibrium constants here, only this time we just had to remember to double the number of ions because of that 2-to-1 ratio. So I'd like you to try some practice problems in your workbooks right now. There's some practice problems on page 170 of your workbooks. Pause the video for a minute while you have a chance to go through the questions, and I'm going to just kind of leave the first couple of answers up on the board to get you started if you're having problems, and then we'll go through 2 and 3 together as a class. So you can pause the video here. And then there's solutions for C and D as well. So you can pause the video here, just make sure everybody in the class is on the right track with those 2 questions. Then we'll go through 2 and 3 together just to make sure everybody's on the right track here. So it says a student prepares a saturated solution. Again, we're talking saturated solutions, so we know we have an equilibrium. And this time we have magnesium hydroxide. You'll notice we've got moles in a 500 milliliters of solution. So the first thing I'm going to do is I'm going to change that to a molarity. So I've got my 5.5 times 10 to the negative 5 moles of magnesium hydroxide. I'm going to divide that straight away. 500 milliliters is the same as 0.500 liters. So the molar solubility here is 1.1 times 10 to the negative 4. Okay, so there's molar solubility. Now I'm going to work that into my KSP expression. So I'm going to start with my net ionic equation. You'll notice the 1:2 ratio. So that's where I get the squared from. And KSP, when I substitute my values in, the magnesium is a 1:1 ratio, so it's going to be 1.1 times 10 to the negative 4 moles per liter. When I put the hydroxide in, I'm going to have to double it, so it's going to be 2.2 times 10 to the negative 4, and then I'm also going to square it. So I go ahead and do the math on that one. I get KSP is equal to 5.3 times 10 to the negative 12. Okay, question number 3 is very similar, except for this time I'm given the grams of solute that remained. So you'll notice that a student here has figured out the molar solubility. They've taken a saturated solution, and what they've done is they've taken a specific volume of that saturated solution and they've just boiled off all of the water, or they've evaporated all of the water. And you'll notice that after you've evaporated all of that water, the salt crystals are left behind. So they've weighed the salt crystals and they find that 0.16 grams of that solute remains. So again, we're going to calculate molar solubility from there. I'm going to take 0.16 grams of MgC2O4, magnesium oxalate. I'm going to turn that into moles. So I've got 1 mole, and I'm going to look at the periodic table, add up the molar mass. I get 112.3 grams per mole. And then because I want moles per liter, I'm going to divide by the number of liters of solution that they evaporated. So I'm just going to kind of convert that to liters in my head, 0.150 liters. And I can find that the molar solubility there is 0.009428 moles per liter. Now I'm going to look at my net ionic equation, get my magnesium oxalate. Now we don't see oxalates all that often so far in class anyway, so you can find oxalate on your chart, on your ion chart there if you want to take a look at it. But it has a -2 charge. So this time we've got a nice 1:1 ratio. KSP is equal to the concentration of magnesium ions multiplied by the concentration of the oxalate ions. Now I'm going to substitute that 0.009428 moles per liter for both of these because we've got that 1:1 ratio. KSP is equal to and I'll do the math on that, and I get 9.0 times 10 to the negative 5. Again, when we're talking KSPs, no units. When we're talking about molar solubility, you'll notice that we have a capital M there. So the molar solubility is how much can dissolve to make, how many moles can dissolve to make a saturated solution. KSP, on the other hand, tells us the ratio of our products and reactants. So they're slightly different concepts. Okay, in the next step here, we're going to look at working backwards. So this time we're going to calculate molar solubility when we're already given a KSP value. And you'll notice that there is a nice new chart in your data booklet, exciting day when we look at a new chart in our data booklet, that looks like this. It says solubility product constants at 25 degrees Celsius. Now, the 25 degrees Celsius is important because we know equilibrium constants change if you change the temperature, and temperature is the only thing that will change that constant. So these are all for 25 degrees Celsius. Most of these have low solubility in water, and you'll just kind of see them listed alphabetically. Their formulas are there too, which can be really handy when you're trying to write out net ionic equations, so look for that as well. And the KSP value shows us kind of a ratio, and it shows us how many ions are created. So if we have a high KSP value, it usually shows that more can dissolve in that water. Whereas if we have a very, very low value, it's really not very soluble. So if I'm looking at kind of one of my least soluble things, I can look for something that's got this really, really like minus times 10 to the negative 39, iron 3 hydroxide is really not very soluble because not much will dissolve. So that exponent can kind of tell you a little bit about how much will dissolve in water. So calculating molar solubility, you're going to need that chart, excuse me, from your data booklet. So it says calculate the molar solubility of iron 2 hydroxide from its KSPs. Now you also want to be really careful about making sure that you get that Roman numeral as well, because iron 2 hydroxide and iron 3 hydroxide are very, very different on the chart. Iron 3 hydroxide has very, very low solubility, and iron 2 hydroxide, you notice, is still low solubility, but not nearly as much as the iron 3. So pay very close attention to those Roman numerals right after the word there. Okay, so I'm going to take my net ionic equation again. So I've got FeOH2, and I'm going to show the net ionic equation for that. My iron has that positive 2 charge, so that's what the 2 shows us there. And I have 2 hydroxides for every 1 iron ion. So I have a 2-to-1 ratio here. Now when I write out my KSP expression, KSP is equal to the concentration of the iron multiplied by the concentration of the hydroxide squared. So that coefficient becomes a power. Now you'll notice that we know the value of KSP. We can look that up on the chart. I got 4.9 times 10 to the negative 17 equals the concentration of iron ions multiplied by the concentration of hydroxide ions squared. Now we've got 2 unknowns here. However, we also know we've kind of got a ratio here. So if you think about it, when we had molar solubility and we're given molar solubility, and I'm just going to use S to represent solubility here, we know that if we knew the molar solubility, then I'm going to have a 1-to-1 ratio with the iron ions and the iron 2 hydroxide, but a 2-to-1 ratio with the hydroxide. So it's like taking that molar solubility and multiplying it by 2. So I'm going to use S's here, and I'm going to plug them in the equation so that I can only have 1 unknown, so I can actually solve this problem. So I'm going to put S in for the Fe2+, and I'm going to put 2S in for the hydroxide, and then it's again squared. So I'm going to try and work out some of the math here. You'll notice that this 2, this squared, applies both to the 2 and the S here. So I've got 4.9 times 10 to the negative 17 is equal to S times 2 squared is 4, and S squared is S squared. So I've got S times 4S squared. 4.9 times 10 to the negative 17 is equal to, we'll combine all of our like terms here. So S times S squared is S cubed. So I get 4S cubed. So now I'm going to do some math to solve for S. First thing I'm going to do is going to divide both sides by 4. So the 4's will cancel out on the right-hand side there. So I got 1.22 times 10 to the negative 17 is equal to S cubed. And then I'm going to cube root both sides. So solving for S is the molar solubility there. I get S is equal to 2.3 times 10 to the negative 6. And this time I do have units because it's a molar solubility. I'm going to use that capital M or moles per liter as my final answer. Okay, so there's a 2-to-1 ratio, and you'll notice with 2-to-1 ratios, we end up with KSP is equal to 4S cubed. So we're going to find that as kind of a pattern in some of our problems whenever we have a 2-to-1 ratio. So we'll do one last question here. And this time we're going to look at a 1-to-1 ratio. It says what mass of silver bromate would need to be dissolved in 275 milliliters of water to create a saturated solution. So first off, I'm going to look up sodium bromate or silver bromate, on the chart here. So silver bromate is the line AgBrO3, and it's 5.3 times 10 to the negative 5. So I'm going to start with my silver bromate, AgBrO3. My net ionic equation, I'm going to split it into ions. And I'll write out my solubility product expression, KSP. This time I have a 1-to-1 ratio. So if my molar solubility was here, I'd say that the number of silver ions that are split off is in a 1-to-1 ratio, and 1-to-1 with the bromate as well. So this time KSP is equal to S multiplied by S. So my KSP, S multiplied by S, same base, we're going to add the exponents, so it's going to be S squared. So I'm going to substitute that KSP from the chart, 5.3 times 10 to the negative 5 equals S squared. Our math is actually easier this time. All I have to do is take the square root of both sides. And the molar solubility of silver bromate is 7.2 times 10 to the negative 3, and that's moles per liter. Now the question isn't quite done yet, because now I have molar solubility, but it's asking for the mass of silver bromate. It's asking for what mass of silver bromate would need to be dissolved in 275 milliliters of water. So again, we're going to need to do just a little bit of stoichiometry here. I'm going to take my 7.2 times 10 to the negative 3 moles of silver bromate, AgBrO3, per liter. I'm going to multiply by the number of liters, so I've got 275 milliliters of water, so that's 0.275 liters. My liters will cancel out. And the last thing I'm going to do is I'm going to multiply by the molar mass of